activation energy, that is where you are missing that any nucleation event and a growth event needs diffusion. This aspect if you miss out, we will think that the whole nucleation is just driving force related, is not it. That is the reason why the whole of TTT diagrams come. Why do you have a TTT diagram which has a C shape? The C shape of the TTT diagram comes from the diffusion problem, is not it. If you remember this C shape, which for example we talk about austenite to perlite transformation, why is this shape? This is what we call it a start of transformation, this is what we call it as the end of transformation. So that means this is nucleation, this is the end of growth. Why is this it has a C shape? Basically because the nucleation and growth even for that matter nucleation itself is a combination of two. One, the driving force delta G, the delta G is important and diffusivity D is important. In fact, if you go a little deeper, nucleation kinetics, unfortunately we are not really dealing with nucleation kinetics, you remember you have an expression like this. You have an expression like that. This part you people are forgetting, that is very important part. Please read Reed-Hill, physical metallurgy, Reed-Hill, nucleation. There is a wonderful chapter in Reed-Hill. I thought all of you should have read at the BTech level. If not, please go through that chapter, and this is very crucial. And if you look at only this part, then you are right. You are right that as I keep on going to higher and higher intercooling, I get higher and higher driving force. If the driving force is higher, in principle my activation energy should be lower. So the same thing when you are talking about liquid going to single phase alpha or liquid going to two phase mixture, we are assuming that diffusion does not play a role. But we know that if a liquid has to go to a two phase mixture, it needs long range diffusion, but if liquid goes to a single phase structure of the same composition, then it does not need long range diffusion, it needs only short range diffusion. And a short range diffusion always needs lesser activation barrier. That means this part is smaller for short range diffusion, this part is going to be larger, this particularly this is going to be larger for long range diffusion, and that is the reason why this dominates. You are right, this is also there, delta G star is going to be higher if the delta G is going to be lower. If the driving force, so if I look at liquid of some particular composition C1 going to alpha of C1, or liquid going to liquid of Cl plus alpha of C alpha composition, if this delta G is smaller, then if this is smaller, then delta G star is larger here. This is delta G star only for the nucleus, that is it. So this is what is in fact if you carefully look at it, what is delta G star? It is delta G for R star. Okay. So actually it is speaking what is the change in free energy when a liquid goes to a solid with the solid having a size of R star, that is what we call it as delta G star. But because that is a higher, we call it as an activation energy. The overall activation energy for nucleation, you have to consider a combination of these two. This is clear. So as a result, we need to consider that aspect, and definitely this transformation will have a lower activation barrier. This is even true when we come to solid state transformations. We will see why is that when I take let us say age hardening or precipitation hardening, you take aluminum copper standard example. In an aluminum copper, when we are doing precipitation, what comes out first? GP Jones we say. We do not, what is the stable state there? Theta. Theta is the stable state. So definitely the delta G, the driving force for the supersaturation to transform to theta must be the highest. because that is the equilibrium state, but it does not happen. Even you see in the cases of steels, when you take a steel martensite and temper the martensite, I do not know how many of you remember, what is the phase that comes out during tempering? It is epsilon carbide, it is not the cementite which comes out. Why is that? Obviously epsilon carbide does not stay, if you do the tempering at higher temperature or for longer times, this epsilon carbide vanishes. Similarly the GP zones vanish, if you do aging for a longer time, GP zones turn to theta double prime, then theta prime, then finally the theta. What does that mean? That means all these initial stages are only transient phases, transient metastable phases, and the stable phase is the theta. Similarly in case of steels, it is the cementite which is the stable state, but cementite is not able to come. We will see when we come to solid state what are the further complications that you get for precipitation or for the phase transformation. In case of liquid to solid, which is what we are now dealing with, in a liquid to solid there is only one barrier for transformation. What is that barrier? It is the surface energy, and when you talk about the solid state, you get additional barrier, that is a strain energy. We will talk about that. That is when you will realize why do you need this to come out. We will talk about precipitation later. So you need to understand that it is just not the driving force that always leads to. So when we come to, for example, we will definitely talk about this later when we are going to talk about solid state transformations and go in a later little detail on that. At the moment we will continue with our liquid to solid that we are talking about.
Sir, in the above expression, can I consider delta G star as the activation energy?
Yeah, that is what I am telling. Delta G star is the activation energy for the nucleus to form without considering the diffusion. Even for the nucleus, what is a nucleus? Nucleus is nothing but a cluster of atoms with an R star size. Am I right? This is what we call it as a nucleus. And for a cluster of atoms of R star size to evolve from the liquid, you need atoms to move, atoms to come together and form that R star. These atoms to come together to form R star, you need some diffusion that is required, and that is delta GD.
So then when delta T is more, how I get fine grains?
That is what I am telling. So when I say delta T is more, you get fine grains, we are always making an assumption that we are in this domain. There is an inherent assumption which one has to be very, very careful, that I am in this domain. If I am in this domain, as I keep on increasing the delta T, that means cooling rate. If I increase the cooling rate, I am increasing the undercooling. If I am increasing the undercooling, I am increasing the delta G. So you can see that cooling rate is proportional to delta T, which is proportional to delta G, and as a result delta G star decreases, and the temperature here in this domain is high enough for the delta GD not to be really dominating. So because we are still not in a low temperature domain for the diffusion to start dominating. So diffusion still can occur because we are at high temperatures, and as a result it is this which now decides what is your nucleation rate, not the delta GD which decides the nucleation rate, but it is delta G star which decides the nucleation rate in this portion, and that is the reason why you will see that finer grain size. And most of the cases the cooling rates that we adopt in when I talk about sand mold or a permanent mold or a water cooled copper mold, there the undercoolings that we are talking are not really the kind of undercoolings that can really bring the liquid below this domain. If you really want to get the undercooling below that domain, you need to use much higher cooling rates. That is where you will always see the diffusion dominates, and that is the reason why you will actually see even glasses forming. The fact that a glass forms from a liquid is an indication that nucleation is not able to happen. The atoms are not able to come together to form that nucleus, and the nucleus is not able to grow. If that can happen, then why will glass come out? In fact, long back Turnbull has made a profound statement that every liquid would like to become a glass unless crystallization intervenes. It is this crystallization which is coming in the way, otherwise liquid likes to become a glass, because liquid and glass are of similar structure. Nothing need to change for a liquid to become a glass, but it is the crystal formation which is commonly observed. Why? Because in most of the metals and alloys, the crystal structures being so simple that they can easily nucleate. The atoms coming together forming an FCC cluster or a BCC cluster is easy, but if your cooling rate is so high that even that cluster is not able to come together for forming of a nucleus, even you do not see pure metals also people have seen glasses formation. Pure silicon people have quenched at very high rate and they have seen it becomes a glass. Pure nickel people have shown at as high rates of 10 to the power 12. Do you know how do we reach this kind of cooling rates? Did we talk any time? 10 power 6 is what you get when you do what is called melt spinning or gun quenching. How do you reach this kind of cooling rates? That is what I said, melt spinning is the one where we talked about it, where you take a wheel which rotates at a certain speed like 3000 4000 rpm and you pour the liquid metal on this, and then the moment a droplet falls, because it is spinning, it is like a spinning. So, because this wheel is spinning, it pulls this droplet along with the wheel. So, the droplet sticks to the wheel and then gets pulled. As a result, the droplet gets converted into like a sheet of metal. It is like a rolling without a second roll there. So, and as a result you get flakes, every droplet becomes a flake. And if you have a continuous flow of liquid, in principle you can have a continuous sheet of, people have produced even up to almost like 1 feet width. I mean it is almost like a continuous casting, excepting that in a continuous casting you always have two wheels. It comes out as a slab, the liquid metal goes, and then it is like rolling. Here there is no such kind of a rolling because there is no second wheel on top of it. So, the liquid, only thing is you control the flow rate of the liquid and control the speed of this in such a way that it comes out as a continuous ribbons, and people have made kilometers of ribbons like this, a particular type of alloy which is iron based metallic glass, where large number of people have worked on it. So, here you get a cooling rates of the order of around 10 to the power 6 and 10 to the power 12, anybody knows? Laser. If you use laser, for example, have you heard of picosecond laser? No, picosecond laser, nanosecond laser, okay, pulsed lasers. So, in pulsed laser, a picosecond laser basically means 10 to the power minus 12 seconds it is active. So, imagine a solid surface on which you have a laser which falls on it, and it is active only for such a short time. Within that time the laser will melt that surface, very small volume, maybe a few micrometers of volume, and then immediately it solidifies. And if you assume that this melting and solidification is happening within this particular period, it melts, of course there will be a time lag. So, actually it may not happen exactly within that time, but if you assume that if it melts, and think of an aluminum being melted, let us say, and aluminum if it is melted, what is the temperature to which it goes? Approximately let us say 1000 Kelvin, and then from 1000 Kelvin it cools back within that time, because the laser is active only that period and it is shut off. So, that is what is a pulsed laser. So, then within that period again it has to cool back, and how does it cool? The whole metal itself acts as a quenchant. In a slab of a metal, only a few few micrometers cube of a region is getting actually melted, a small pool is melted. So, rest of the metal quenches that particular liquid. So, you get the liquid brought back from 1000 degrees to room temperature within this particular period. And if you consider that, if you think that 10 to the power 3 is the temperature change that is taking place, and 10 to the power minus 12 is the time. This is the t and this is the time, and you would see the ratio gives you 10 to the power 15 Kelvin per second. In principle, theoretically one can get this. Of course, practically it is difficult, that is why I said 10 to the power 12. If you use a picosecond laser, because there will be a small time difference, it has to heat and then cool. So, if you consider a small difference, people have been able to achieve these cooling rates. This much temperature difference in this much time, temperature divided by time is what is the cooling rate. So, in principle you can get that cooling rates, and with that people have shown that even pure nickel can be made into a glass. People have made glasses like that. That means your temperature, your time available is so short for the atoms to even form a R star. It does not mean that clusters do not exist in the liquid. Clusters are there, but their size is not equivalent to an R star. They are like embryos. So, they are not able to reach the R star size, and if they do not reach the R star size, obviously you will not have a nucleation. So, that is what is the whole concept of the glass formation, and anyway we will talk about the glass formation later, and this aspect also we will talk about it when we are going to talk about glass formation. Okay, let us continue where we have left last class. In the last class we were talking about the T naught curve, and we talked about a curve such as T naught, and we said any alloy that you choose, if you can bring it below the T naught, then we are at a condition where there is a possibility of partitionless solidification. I said there is a possibility of. So, whenever I say you bring it to any undercooling below that, if your undercooling is so high, you bring an undercooling up to this level and you come actually below the Tg, there is even a possibility of glass formation. We will talk about it after a while.
Curve is energy of liquid and solid are equal.
Correct.
Here are we extrapolating that curve to the
Which curve? This one?
no, it should be an L plus alpha region.
Yeah, that is what I am saying. When you say L plus alpha region, so for example, if I take this liquid and undercool to this temperature, what should happen to that liquid? Under normal conditions, if the liquid is simply cooled, it would have first formed alpha, and then by the time you reach this temperature, eutectic reaction should have occurred. Now, you have brought this liquid to that temperature, and your Tg for that alloy is somewhere here, let us say. You are above the Tg, but below the T naught. So, liquid has no chance for it to become a glass. You are not at reached the temperature where glass can form. I will also talk about glass formation possibly in the next class. We will know a little more about this Tg concept, but at the moment if you understand that this is above that. So, liquid has to, and at the same time liquid is not stable. At this temperature, according to the phase diagram, what is stable? In principle it is alpha plus beta that is stable at that temperature. So, liquid is no way it has a chance to be stable there. So, liquid wants to transform now. So, how does it transform? To what it will transform is what we are looking at. Again the same concept, if because we are at this temperature, if I extrapolate the T naught curve, I will see that my composition at this temperature is to the left of the T naught. So, there is a possibility that that liquid which is staying there at that temperature has a chance to become solid by partitionless solidification. But if the same liquid is somewhere here, no. Or if I choose another alloy and bring it to the same temperature, this alloy has no chance for it to become a partitionless solidification, because now it is on the right side of the T naught curve, at the same temperature, and whenever we are on the right side there is no driving force for partitionless solidification. So, Li number 1 has a chance for becoming a single phase alpha by partitionless solidification, and that is what it happens. And now if you look at compositions like Li2, what should happen to these compositions? It has no driving force for partitionless solidification, at the same time it is at a temperature where the liquid is not supposed to be stable, because we have brought it to this temperature. At this temperature liquid cannot remain as liquid. So, the only chance for it is, and at the same time it is also above the Tg. So, liquid has only one solution, that it has to become a solid by partitioning. The only difference would be the solid that comes out at that temperature may not be the solid at this temperature. When the liquid is taken, the liquid should give you a liquid plus solid. At this temperature, once I bring this liquid, it has to give you liquid plus solid, either liquid plus alpha or liquid plus beta, depending on the situation and depending on which side of the phase diagram you are. And now which will be the composition of that alpha, which will be the composition of liquid, how will I know? At that temperature, I have brought this liquid to this temperature. At this temperature it has no solution but to undergo a partitioning, and it should have a solidification along with partitioning, and such a partitioning when it is taking place, what will be the composition of liquid, what will be the composition of alpha, how will I get? Let us say if this Li is at this temperature, this Li1 is at that temperature also it is above the T naught, is not it, above the T naught, and if I draw a line at that temperature, horizontal line, it is on the right side of the T naught. So, that means the partitionless solidification is again ruled out. So, that Li will now undergo a solidification by partitioning. What will be the composition of liquid, what will be the composition of alpha at that temperature? How do you see? By not the lever rule talks only about amounts of liquid, amounts of alpha. It is that tie line, and wherever that tie line intersects the alpha and the liquid, that would be the composition of alpha, the composition of the liquid. So, alpha of this composition will come out of the liquid at that temperature, and the remaining liquid will get this particular composition, and that is how you will have a two phase mixture of alpha and liquid. Now, if I am considering another alloy, Li2, and I am saying that this Li2 is brought to this temperature, again the situation of this Li2 at this temperature is similar to the situation of Li1 at this temperature, there is no difference. Now, what will be the composition of liquid and alpha? The only difference is I am now below the eutectic temperature, earlier I was above the eutectic temperature. Now, what will be the the composition of the liquid and the composition of alpha?
Liquid will be that of eutectic.
Why? Liquid is not eutectic, liquid composition is this, eutectic composition is this. Okay. Again draw a tie line, yes. How do, now I drew the tie line now. Now, this tie line, when I extend this tie line, okay, it is intersecting alpha here, beta here. So, but I am talking of liquid and alpha, liquid is giving me liquid and alpha, liquid is not giving me alpha plus beta.
If the alpha composition is that, liquid composition cannot go beyond the composition of eutectic.
So how do you find out the composition of alpha and liquid now? To find out, you need to look at, whenever I am talking of liquid and alpha, I need to look at what indicates the equilibrium between liquid and alpha. What is that particular composition which talks about liquid alpha equilibrium? liquid alpha equilibrium is decided by this line and this line. These are the two which talk about liquid and alpha equilibrium. This is the liquidus, this is the solidus, and this gives you the alpha composition, this gives you the liquid composition. If you want to know what is the composition of alpha and what is the composition of liquid at any temperature, what you need to do is you need to extrapolate those curves. So, you extrapolate the liquidus, you extrapolate the solidus, and the compositions, because what I mean to say is at this temperature, if alpha has to come out of liquid, imagine there is a liquid, inside that alpha is coming out. If this liquid has to be in equilibrium with alpha, it can be in equilibrium with alpha only by this. This is the only line which tells me what is the composition of alpha that can be in equilibrium with liquid. No other alpha composition can be in equilibrium with liquid. So, this whole domain talks about liquid alpha equilibrium. And so, if I want to know what is the composition of alpha that can be in equilibrium with liquid, it is only this composition, because if I draw the free energy curves, common tangent between alpha and liquid, if I draw it, this tells me the composition of the common tangent for the alpha, and this tells me the composition of the common tangent for the liquid. And so, at some other temperature, at a lower temperature, if you want to look at it, basically I extrapolate that, and these extrapolations will tell me what will be the composition of alpha, what will be the composition. So, it is the alpha that comes out at this temperature will be having that composition, and the moment alpha of that composition comes out, the liquid which is remaining will tend to have this composition. And once that happens, now you see the liquid composition is beyond that of the eutectic composition actually, is not it. So, because the liquid composition is beyond that of the eutectic composition, there is a possibility that the remaining liquid which has a richer in B atoms can start nucleating the beta, and there is a possibility that the remaining liquid gets converted to beta, because we are on the B side now, the liquid composition is on the B side now. So, because it is rich in B, the liquid is rich in B, it can easily nucleate beta, which is a beta B rich phase. So, you will see that in all these cases, though the alpha that comes out initially will be of this composition, at some stage you will see the remaining liquid gets converted to beta. So, you will have a situation of beta matrix and an alpha phase, and as you hold for a longer time, as you cool to lower and lower temperature, this alpha slowly changes to the equilibrium composition of alpha, because the moment beta comes out, alpha of this composition cannot be in equilibrium with beta. If alpha has to be in equilibrium with beta, only alpha of this composition can be in equilibrium with beta. So, as a result, the alpha composition shifts from here to here, so that it can be in equilibrium with beta, and you will see that slowly, and because of the composition is becoming lower in B content. So, the some excess B atoms which are available in the in alpha will be rejected out of alpha and will go and join the beta, so that the beta quantity will increase, and then alpha composition will get shifted towards richer A, and that is how the whole process happens. This is all assuming that partitionless solidification is not taking place. If we have a situation where partitionless solidification is not taking place and you are at temperature below the eutectic, if you are above eutectic, all this problem does not happen. Here at this temperature you will hit alpha, and as you cool to lower and lower, the liquid composition changes, and then finally it reaches eutectic, and that liquid will give you a eutectic mixture like any other solidification. But if I have undercooled the liquid to a temperature below the eutectic and solidification is now about to start, what should happen to this liquid? It cannot straight away give you the eutectic mixture, because the liquid composition is not a eutectic composition. You know, please remember, eutectic reaction is an invariant reaction. What is the meaning of invariant reaction? Invariant reaction means everything is fixed. The composition of liquid that can undergo a eutectic reaction is fixed. Every liquid cannot undergo. You may say, sir, this alloy also will have a eutectic reaction, this alloy also will have a eutectic reaction. Why do you say that liquid should have this composition only? This alloy is undergoing eutectic reaction, but the liquid of this alloy which is undergoing the eutectic reaction always has only that composition. Please remember that. If I take this alloy, this is the alloy I am choosing, if I slowly cool, under normal conditions you will have the alpha coming out, and as I come to lower and lower temperature, more and more alpha comes out, and the remaining liquid, its composition shifts towards this and then comes to this particular composition. So, the moment I reach this temperature, the liquid that is remaining inside the liquid plus alpha mixture will always have that composition, and it is that liquid which is undergoing a eutectic reaction, not the liquid with which you have started. So, the eutectic reaction always, the liquid which undergoes the eutectic reaction will have this composition, because it is A rich phase that is coming out, liquid becomes richer in B. If you are on this side, it is beta that comes out first of this composition, and as you come to lower and lower temperature, more and more beta comes, and beta, because beta is B rich, the liquid gets depleted in B, all the B in liquid goes into the beta, and as a result the liquid composition changes, and then once you reach eutectic, the liquid composition is always that. So, whether you choose this alloy or any alloy within the eutectic domain, the eutectic reaction always happens between the liquid of a fixed composition, and that composition is the eutectic composition. So, that is the meaning of an invariant reaction. You cannot have any liquid giving you a eutectic reaction. So, because we are now talking about this liquid, yes, it is again the free energies. If you draw, for example, if I draw what is the meaning of eutectic? Liquid giving you alpha plus beta, that means one phase is giving you two phases, there are three phases in equilibrium, is not it. So, if at that temperature, eutectic temperature, if I draw a free energy composition diagram, I will see that you will have one liquid curve, one alpha curve, and if I draw a common tangent, you will see this. This is the liquid, this is the alpha, this is the beta. You will see at that temperature, if I draw at this eutectic temperature TE, if I draw the free energy composition diagram, I will see a free energy composition diagram like this, where all of them having the same common tangent. And what does that mean? It means that wherever this tangent intersects here on the y axis, I can call this as mu of B in liquid is equal to mu of B in alpha is equal to mu of B in the beta. Similarly, on this side I can say mu of A in liquid is equal to mu of A in alpha is equal to mu of A in beta. That is what is the definition of equilibrium here. The chemical potential of A in alpha, beta and liquid, all of them are equal. Similarly, chemical potential of B in all the three phases is equal. And now what decides that composition? It is this composition. Wherever this common tangent is taking place, the composition corresponding to that common tangent will be the composition of the liquid. So, if you draw these free energy curves at that temperature, draw a common tangent, whatever composition corresponds to the liquid composition of that common tangent will be this composition, and this composition and this composition, this will be the alpha composition, this will be the beta composition, this will be the C liquid composition at the eutectic temperature. That means these three compositions. So, everything is fixed, like we drew a unary phase diagram for H2O. We saw that the pressure and temperature at which all the three phases can exist is fixed, it is not in your hands. Similarly, the compositions of alpha, liquid, beta is fixed and it is not in your hands, it is decided only by the temperature. Now, if I come to a lower temperature, at a lower temperature in principle liquid is not stable. What should happen when I decrease the temperature? What should happen to these free energy curves? They will go up. Which one will go up? Alpha and beta will not go up, everything will go up. This has to be remembered. It is not that liquid only goes up, alpha beta do not go up, it is only the rate at which they move up that matters for us. Okay? Yes, Matthew. Correct. See, the question is, whenever we talk of equilibrium, there is always something called local equilibrium, which has to be maintained, unless you are at such a highly non-equilibrium states that where atoms cannot move at all, like a Martensite transformation, diffusion less transformation that is taking place, or a liquid giving you a glass, that you are at such a temperatures where no diffusion can occur, atoms cannot move, then local equilibrium fails. At all other temperatures liquid tend to have, that is why the moment alpha forms, what happens is a thin, maybe it can be even a monoatomic layer, it can be a 2 atomic layer thickness, but that thickness, within that thickness of liquid around it, it will have a composition which is decided by that tie line. And if you think that the temperature is like very small, like absolute 0 or very close to room temperature, even room temperature, whenever we talk of temperature we should remember what that we are talking about. For example, many of you know that deformation at room temperature for lead, we call it as high temperature deformation, hot deformation. So, with respect to what we are talking, that means with respect to which material where diffusion is easier or faster or not easier, that means with respect to the melting point of that metal we are talking about. Similarly, if we are talking about a material which has a sufficiently high melting point, and if we are talking about at temperatures which are close to room temperature, where this also cannot happen, the liquid, inside liquid atoms cannot move to be able to come to that temperature, that composition decided by the local equilibrium, then what would happen is liquid will not give you that alpha. Even for liquid to give you that alpha, atoms have to come together and form a structure which is an FCC or a BCC structure having this composition. Because now at this temperature, if I simply draw the free energy composition diagram, I have a liquid. Now this is the liquid of certain composition that I am choosing. This liquid, what should happen to it? If I look at it, then I should look at what are all the other phases that are possible. Can I draw the free energy composition diagrams for them? And if I draw the free energy composition diagram for alpha, let us say, I may see that yes, there is a driving force now. Just because there is a driving force, will it form or not is decided by that structure of that particular phase, how complicated or how easy it is, whether it is able to nucleate or not. If it can nucleate, that means the diffusion is able to take place, even if it is localized diffusion, and if localized diffusion can happen, then local equilibrium has to be established. If local diffusion also is difficult, that means short range diffusion is also difficult, then there is no chance of even local equilibrium. Yeah, coring definitely happen, you see, but the thing is the coring we are assuming that you have alpha at each temperature as you go below of different compositions nucleating. This is assuming that our temperature is such that we are above the T naught. If you are below the T naught, there is no question of coring. The alpha that comes out will be same composition as that of liquid, absolutely there is no coring. Okay, clear? Okay. So, coming back to this problem, if we are at a lower temperature, then you would see that all of them are going up. Only thing is liquid will go up faster. Why should it go up faster? Yes, remember G versus T curve, G versus T curve, the slope of it is entropy, and as a result, so if you change the temperature by 1 degree, how much the G will go up is decided by the slope. So you will see that if I decrease the temperature by 1 degree, the liquid will go up faster when compared to solid, because both the solids have a shallower free energy curves, free energy versus temperature curves. So because the entropies are lower, so they will not rise at the same level as the liquid. So as a result, when I decrease the temperature, this starts going up. So that means, and all of them are going up, let us say they go up like this, but this goes up faster. If this goes up faster, then you will see a situation. Now I cannot maintain a common equilibrium between all the three, common tangent between all the three is not possible. The only tangent that is possible, of course you can have three tangents, you can have a tangent between alpha and liquid, you can have a tangent between beta and liquid, you can also have a tangent between alpha and beta. And if you look at which of the tangent is the lowest, which tangent has a lower free energy, you would see the alpha and liquid. The alpha to liquid will be like this, the beta to liquid will be like this, and alpha to beta will be like this. And because the alpha beta free energy, I mean common tangent is below that of the other two, we say that alpha beta is the most stable state. That is why when I come to a lower temperature below this, at this temperature it is alpha and beta which is stable, and that is what you will see. Okay, come back. You see, we our interest is not this, our interest is to see what happens if I take a case of, if I take a case of if I take an alloy of this composition, I have undercooled it to a very low temperatures, and to an extent that as I keep on undercooling it, the T naught curves of the alpha and beta are such that their slopes are such that this composition is not intersecting any of them. If that is the case, when you reach a low temperatures, at that stage where we are just now talking about it, even local equilibriums cannot be maintained because atoms are not able to move, and at such stage this liquid will have a tendency to form a glass. And there is a temperature below which this will happen, and that temperature is what is called a glass transition temperature, and that comes from a concept of, if you draw the viscosity as a function of temperature, viscosity of the liquid, you will see that the liquid viscosity above the melting point is usually of the order of around centipoise. Most of the metallic liquids just above the melting point, if you measure their viscosity, they are all of the order of centipoise, whereas if you take a silicate glass liquid above its melting point, take any silicate glass type of materials, any silicates, and take them above the melting point and measure their viscosities, the viscosities of them will be of the order of 10 to the power 2 to 10 to the power 3 poise. We are all talking of above the melting point, whatever may be the melting point. So that what does it tell you? It tells you that these are highly viscous when compared to metallic liquids. The reason is the 3-dimensional network kind of clusters that are there in those liquids. The silicate clusters that are there in the liquid will make this liquid very viscous, and that is the reason why we always say glass formation in these liquids is easier, because for them to nucleate a silicate solid, crystalline solid, is more difficult when compared to metals. Atoms can easily move because they are less viscous, atoms can move because this is more viscous, atoms are not able to move. And now if I plot how this viscosity changes with temperature, you will see the viscosity changes almost like this. This is starting from about melting point 10 to the power minus 2 to it goes to a temperature level of around 10 to the power 13 to 10 to the power 14 poise, and this 10 to the power 13 poise is a kind of viscosity of solids. Any solids that we talk about, whenever we talk of a solid, the mechanical definition of a liquid is that a liquid which has a shear modulus 0 is what we call it as a liquid. It can easily flow, its shear modulus is 0. So, a solid is the one which shows some shear modulus. So, that is actually related to the viscosity. So, the moment the viscosity reaches that value, then immediately this liquid has to become a solid. So, it is mechanically a solid, it has a shear modulus now, but it structurally is a liquid, because you are at a temperature where there are no atomic arrangements can take place, atomic rearrangements. So, atoms remain where they are, that is why we call it as a configurationally frozen liquid. So, a glass is what we call it as a configurationally frozen supercooled liquid. So, the moment you bring the liquid to this temperature, which is what we call it as Tg, you suddenly see that the liquid freezes into a solid, but into a solid which has structure similar to that of a liquid, and that new type of solid which we have not seen before, because most of the solids that we know are all crystalline solids. Now, you have a solid which is non crystalline, which has a structure similar to that of a liquid, we call that as a glass. This is what is one way of looking at glass formation. We will also possibly look at the other way of looking at how the glass forms, and I can achieve this particular thing by basically a very fast cooling. If I cool, because we are all talking of undercooling the liquid, please remember, I am not simply cooling the liquid, I am undercooling. So, that means I am able to achieve, if this is the Tg for this phase diagram, if I can undercool the liquid below this Tg and at the same time not being able to intersect the two T0 curves, then I will see that particular liquid will, because at this temperature partitionless solidification cannot occur, because I am above the T0 for both alpha and beta. So, the liquid is able to remain as liquid, it is not able to become a partitionless solidification to single phase alpha or single phase beta. Now, what should this liquid can happen? The liquid can only undergo solidification by partitioning, or for that to happen, if diffusion is difficult, the only choice for it is to become a glass. And because we are at temperatures where diffusion is not able to take place, because liquid has already configurationally frozen, because atoms are not able to move. So, as a result, that particular liquid at that temperature would become a glass. If I am at any temperature here, if I have undercooled the liquid to that temperature, it can still become solid by partitioning. It can start giving a alpha or beta, whichever has a lower activation barrier for nucleation, it will start forming that, and then it will continue. But the moment I bring it below the Tg, this liquid has no chance but to become a glass, and that is where we start defining what are called deep eutectics and shallow eutectics. There are some phase diagrams which are like this, let us say, where the T0 curves look like this, they intersect with each other, and if the Tg is somewhere here, by the time the liquid eutectic liquid is brought below the Tg, it already intersects the T0, either the alpha T0 or beta T0, and once that happens, we will see either alpha or beta comes out. Okay. We will continue this later and see more of how to understand the glass formation.